Okay, hello everybody. Welcome to the Multiphysics Channel. Today is the fourth episode of the Pro series, and we are going to talk about solvers in multiphysics simulation. In today's section, we talk about an overview and the principles behind the solvers, and in future we will go more into details about the solvers and about the algorithms and some tips about the different solvers and different algorithms in the solvers. I'm Kamran Iranshai, very honored to be your host today. A short introduction about me is that I'm a mechanical engineer. Currently, I'm doing my PhD at Empa-TV and ETH Zurich, and I know myself as a nature lover. That's why I provided here some suggested hiking routes in Switzerland for you. If you are in Switzerland, you can try them. If you are not in Switzerland, maybe one day that you come to Switzerland, you can try these routes. And below you can see two truths and one lie about me. Maybe you can guess which one is the lie. And with that, we will go for the first question. That's why should we know about solvers? Why solvers are important for us? There are different ways to answer that question. I chose three answers for that based on my point of view. The first thing is that solving is the main goal of a simulation study. So when we have a simulation study, we always follow this procedure. We identify a problem, a physical problem, and then we model that problem in such a way that we can apply our physical or conservation equations and solve the conservation equation for that problem. So whatever we do in the pre-processing is to to make the model in such a way that we can solve it. So that's the main goal of simulation studies, solving the conservation equations for physical problems. And another thing is that one of the difference between different softwares, either commercial or open source software, is basically selecting the solver. Yeah, there are different other things like being user-friendly and other maybe features, but one of the other important things is that how efficient they are in solving that specific problem. That's why it makes a difference, for example, in different areas like structural analysis, people, they go for ANSYS or Abacus or other programs, or in CFD they choose COMSTOOL, OpenFOAM, and for example ANSYS Fluent, because first they are more user-friendly in that specific area and they are more efficient in solving those kind of problems. And the third one is that there are some problems in the simulation that we do that maybe it's also good to check solvers. For example, here I provided two problems that maybe usually we face. For example, first of all, if you're out of memory, it means that when you're out of RAM, your RAM is not enough. For sure, the first option is that you can increase your computational power to have a more powerful computer. But if that's not an option for you, maybe it's easier to go for simplification. So you can simplify your problem, reduce the degree of freedoms, by which I mean lower the discretization, go for coarser mesh, reduce the geometry complexity, and etc., etc. But then you can also look at the solver. We will see in this session that how choosing a solver can impact the RAM occupation. The other problem is that maybe sometimes you don't get convergence. For sure, again, you should check other things like checking the boundary condition, checking the discretization, all the schemes that you have there. And then maybe also it's also possible to do some adjust some solver setting, then you can get convergence. So for example, if you sometimes increase the iteration number, you can maybe get the convergence. I will talk about this one in this session. So to know about the solvers and how they work, we have to look at behind the scene of a simulation study. Usually especially when we are working on with the commercial softwares, we just click a button or we just fill some blank area, and we never get to know what happens behind the scene of a simulation study. That's not a problem for the people who are doing coding, because they have to know about them and they have to know different algorithms. But usually or sometimes we forget when we are working too much with commercial software. That happens to me as well. So let's have a quick look to the behind the scene. So we have a geometry, we have a physical problem, we make a model of that, and we have a geometry. always we have conservation equations that we want to apply to that geometry. And these conservation equations are in this general form that you can see. But this is highly nonlinear, and we cannot solve a nonlinear equation. So we have to linearize them, for example, with Taylor series expansion, and then apply these linearized equations to the discretized geometry, as you can see here, to the different, each node that we have. And then as a result of applying those linearized equations on these nodes, I will have a system of equations, as you can see there, for each node. And when I gather them, I will have a system of equations. And if I put all of them in a matrix formation, I will have a matrix like this, which first one is called A, which is the coefficient matrix. The second one is the unknown matrix called X. And the third one is constant matrix, which I call it here B. So that's important to know. In all the simulation that we do, in structural analysis, CFD, other areas, we always reach to this point that we have a huge matrix like this that could be with millions of elements based on the degree of freedom that we have. And we have to solve this matrix. So now the question is that how to solve this huge matrix. The first thing that comes to mind is that let's use a direct method. So here we had A multiplied by X is equal to B. So the direct method for that would be like X is equal to A inverse multiplied by B. It means that I have to solve all the elements, all the equations at the same time. But the problem is that to solve all this operation at the same time, I always have a problem with memory. So I will be out of memory because I have to do a lot of operation at the same time. So mathematicians, they provide a solution for that. They said, okay, let's go to restructure the matrices in such a way that we reduce the operations. By reducing the operation, it means that let's restructure it to have more zeros in our matrix. Then we don't solve for the zero elements, we just solve for the non-zero elements. So the ideal condition would be that we go for a diagonal matrix like this, that we restructure whole the matrix that we had and go for diagonal matrix like this. And we have here only the elements on the diagonal part, and the rest are zero. So all the equations are decoupled, and it's easy to solve, less operation to do, and maybe it's easier to solve. But this is the ideal condition. To reach to that ideal condition, they provided different. For example, here I provide like 2-3 of them, like Gauss elimination, LU decomposition, that you structure your matrix in such a way that you be as close as possible to this diagonal matrix that you have. But the problem is that this is not always possible to form such a matrix from our first matrix. And sometimes in direct methods, we have a singularity problem. It means that we cannot solve the matrix because of the singularity problem. So I think everybody agrees that having a rough estimation of our results is better than having no result. That's why they introduce iterative methods. But what is an iterative method? It's basically a guessing game. Let me provide an example for you to maybe it's easier to explain it with an example. Imagine that I have this simple equation, this quadratic equation, and I want to solve it for positive x. If I put it in matrix formation, it will be something like that. So just imagine the first equation now. And the direct method for that is that using this formulation that all of us, I think we know this formulation. And then as a result, I will have this exact value for x, for the positive x that I had. But let's say I don't know this formulation, or I'm too lazy to do all this operation. My memory is not enough for doing all this operation. So what's the next option for me? Or we can say what's the lazy option for us? Is that we just guess. That's the iterative method. That's this simple concept of the iterative method. So as a first case, for example, I put x is equal to 0. In the left-hand side of my equation, I will get 0. And in the right-hand side of my equation, which was the constant matrix, I had 2. The difference between the left-hand side, which is as a result of my guess, and the right-hand side is -2. This is exactly what we call error or residual in our iterative methods. That's the error or residual that we set in our simulation. And it indicates for us how precise we want to have this guessing game. We want to have the final result. For example, here I set the absolute value of my residual should be less than 0.1. It means that do this iterative process until you get a residual less than 0.1. If you look at now, I have -2, which absolute value will be 2, so it's not less than 0.1. So I have to continue. But because it was a negative value, I have to increase my initial guess. My previous guess was 0, and the next guess would be something like 1. If I put 1, the residual would be 2. Again, it's not less than 0.1. I have to continue because it's a positive value. So it means that I have to, next guess should be something less than 1. So something between 0 and 1. For example, I go for 0.5, and then I continue this process until, for example, at 8th iteration, I have a residual which is less than 0.1. That's good. So I'm satisfied with that. And that will be my x, which is equal to 0.55. I just remind you the exact value was something like 0.56. So it's a rough estimation of that with the iterative method. It's already satisfactory for me. That is the basics behind the iterative method. It's a guessing game. I'm just insisting on that. But instead of that simple equation, I have to solve for all the equations, all the elements on this matrix that I had. This is the iterative method. And all the methods that they define in the iterative methods, like Jacobi method, Gauss-Seidel, SOR method, etc., 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 they are just to make it more efficient, to just make the next guess more efficient. For example, just let me give you an example here. If you look at the third and the second guess, I see the residual in the second guess is 2, and then in the third is 0.25. So it means that my actual value is closer to 0.5 than 1. So if I was like smart, my next guess would be something close to 0.5. That's more efficient way. I can get the convergence faster. So one of the solutions that they can do for make it more efficient to weight the next guess based on the previous residual. Then, for example, this was just an example to let you know how we can make this process more efficient. But all the iterative methods that we have, they can be categorized in 2 different groups: fully coupled and segregated steps. What happens in the fully coupled is that I have a first guess, I put in my equations, and I solve all the matrix for that guess, check the residual, it's not satisfactory, go to the next guess, solve for all the matrix, check the residual, and continue this process like that. But what happened in segregation? The question is here is that, again, I have to solve for all the equations for that guess, which is quite tricky because, again, the limitation of the memory comes here. But in segregated steps, the concept is that I subdivide that matrix. For example, let's say in 3 different parts. Then I put the first guess, solve for the first part, then go to the second part, then go to the third part, check the residual, it's not satisfactory, next guess, and continue this process. This is the difference between fully coupled and segregated steps. So with fully coupled, what's the difference between them? With fully coupled, I will have more robust convergence. It's easier to get convergence in a less iteration. I mentioned because, but in each iteration, I will have more operation to do, so more memory in it needed for each iteration. And it's mostly suitable for 1D or 2D problems. But in segregated steps, it requires relatively less memory for each iteration. But as I mentioned, so the number of the iterations should be more. And it allows flexibility in solution. For example, I can choose this part, I can subdivide the matrix based on the physics that I have. For example, imagine that I have like airflow and then heat transfer. I first solve for the airflow and then go for the heat transfer. But as I mentioned, more iteration is needed, and sometimes we have problem in convergence with segregated steps compared to the fully coupled. There are different reasons for that, but one of the reasons could be inflated error. For example, when I solve the first part in segregated, I solve the first part of my matrix, I have some errors associated with that because, for example, like truncation error. And I take all these errors to the next part, accumulate with the errors that from that part, and then I go to the next part and then continue this process. So as a result, I will have like inflated errors that maybe it makes some problems for my convergence and then my solution diverge. So it's suitable for 3D simulation, which we have more operation. But let me explain something here. It's always a trade-off between the complexity of your simulation and the computational power that you have, the memory that you have in your system. If I have a powerful system, if I have a supercomputer, and my for my even 3D models, which is quite not that complex, not for that system that I have, I would always use fully coupled because I don't have a limitation in memory, so I can have it faster and it converges more robustly. So it's always a trade-off between what you have as a problem and the facilities that you have, what is your machine. That was how I categorized, and mostly people categorize the iterative methods, but there are also other categorization. For example, in ANSYS Fluent, they categorize them based on pressure-based and density-based solvers, which is based on the flow regime. For example, for incompressible flow, we use pressure-based, and for compressible, we use density-based. But if you look at inside this pressure-based and density-based, you still you can see this. They divided them based on segregated and coupled. So I think segregated and coupled is the best way to categorize that. Let's go to this example and apply what we learned so far. Here is an example of my simulation that is a model of electrohydrodynamic drawing in which we have an airflow is generated by the electric field, and we want to dry some materials like fruits and vegetables that are like on that mesh with this airflow which is generated by the electric field. So you can see we have different physics here: electrostatics, space charge, ions that move towards the collector, airflow, air and vapor, dehydration in porous media, and all this physics. So it's a complex problem, and I have to solve these equations, all these equations for this physics to get the answer. So that's a question for you. What do you think is what's the proper solver here? Maybe you can think for a few seconds. Based on all this physics that we have and this complex geometry, there are different ways to go, but I chose two ways. First way that I did is that I separated the physics with coupled solver in each. For example, I just solved for the electrostatics. Let's go back here. For just these equations, I just solved these equations, but with fully coupled solver. Then as a result, I had this output, which is input of the next physics, and I solve for the next physics with fully coupled, and then again, I go to the next physics. So that's what I call it, separated physics with fully coupled solver. As you can see here, for example, in each physics, I deactivated segregated solver and then activated fully coupled, because I think when I divide it already into the different physics, it's already I already reduced the number of operations, so I don't need to go for a segregated again. The other way was to couple all the physics to solve for all the physics, but with segregated solvers. And if you look at all these two ways, actually they are segregated because I somehow subdivided whole the domain that I had, whole the operation that I have. So both of them is segregated. Why? Because I had limitation in the RAM with the machine that I was using that time. So that's basically it. And these are the highlights of this episode. Choosing a proper solver matters, especially for pro modelers, because sometimes we have to do more, we have to adjust some settings. And so far we learned that we have two types of solvers, direct and iterative, and in iterative methods, we have fully coupled and segregated steps. In the next topics, we will talk more about algorithms and some tips about different algorithms that we have in our simulation, what's the difference between them, and how we can use them in specific problems that we have. So you can check out our website, Multiphysics Hub, and if you want to have your own episode, you can contact Donato Rubinetti. And if you have questions about these solvers, you can always contact me. Thank you for the attention, and thank you for this session. If there is question, I'm available.